We often trust our eyes to tell us the truth, but the environment can easily distort our surroundings. Take this truck shimmering on a hot highway. It looks like it's submerged in water, but it's actually a trick of the air. Rainbows offer a similar deception. What appears as a solid arc of color is water droplets catching and splitting light into its constituent parts. You cannot touch a mirage, and you cannot walk to the end of a rainbow. These aren't physical objects. They are the visual output of light moving through the atmosphere in precise ways. To create these effects, light must undergo constant refraction, scattering across the sky, or bouncing through the air in a process called total internal reflection. Out in the open air, these are simply packets of electromagnetic energy. They move in chaotic, invisible waves, long before they are organized into the images we recognize. How exactly does this energy cross the threshold into our biology to be rebuilt into a crisp, colorful reality? This anatomical map shows the point of entry. The incoming light wave makes its first contact with the human body at the cornea, the protruding, transparent barrier at the front of the eye. While we often think of the lens as the eye's main tool, the most significant bending of the light occurs right here at the surface of the cornea. Once inside, the wave passes through a fluid called the aqueous humor and reaches the pupil, the dark opening at the center of the iris. The iris acts as a mechanical muscle. It functions as a dynamic aperture, constantly shifting to regulate how much light is permitted to enter. In bright environments, the iris contracts the pupil to shield the internal sensors. In the dark, it expands the pupil wide, pulling in every available photon. Nocturnal predators demonstrate the scale of this adaptation. An owl's pupils can expand to cover almost the entire eye surface, allowing it to hunt using the faint glow of starlight. The front of the eye is a self-regulating gate. It meters the external physics of the light before passing it deeper into the body's hardware. Once regulated, the beam of light strikes the crystalline lens. This lens is remarkably elastic. Through a process called accommodation, the surrounding ciliary muscles can physically warp the lens to change its shape on the fly. When these muscles contract, the lens grows thick and compressed. This creates a high converging power, allowing the eye to pull nearby objects into sharp focus. To see distant horizons, the muscles relax and the lens pulls thin. This reduces the converging power, ensuring the image lands precisely on the back wall of the eye. When this mechanical focus misses, failing to land perfectly on the back wall, the resulting blur is what we call myopia or hypermetropia. If the focus is correct, the light finally hits the film of the eye, the retina. Here, two specialized cell types wait. Rods are sensitive to dim lighting, while cones interpret the bright color spectrum. This is the moment the transformation occurs. Raw physical energy strikes these cells and is translated into a biological, neurological perception. Human sight relies on an unbroken chain of events, where light from the sky meets the engineered surface of our own anatomy. It is a journey from atmospheric scattering and corneal refraction to the flexing of ciliary muscles and the firing of retinal cones. Because our vision depends on these biological structures, our ability to decode the world around us is vulnerable to the health of the machine. Maintaining this system, specifically the clarity of the lens and the sensitivity of the cones, requires a constant supply of specific nutrients. The colorful world we experience is a delicate outcome, requiring a perfect alignment between the physics of light and the physical health of the human body.